Hello, I'm David Porter, and today I'll be presenting with Angel Mancebo, who is in the room, who'll be running the video and chat and fielding questions. And today we'll be presenting a tutorial on data storage and workflows, and specifically the tools and resources that are available to you as researchers here at the University of Minnesota to facilitate your workflows and enable your research. So we'll start with basically some background on the different kinds of storage that are available, the pros and cons of using them, and what their properties are. Then we'll go on to specifically the storage that's available at MSI, and there's a variety of options that you have available. We'll discuss their properties. And then we'll go on to how you go about using them, accessing them through the various utilities and interfaces that are available to you. And then I'll solidify this with some use cases at the end. So to begin with, generally today, there are two primary kinds of storage that are available, whether you're at MSI or at any major computing center. The traditional one is thought of as usually referred to as POSIX compliant. And this is what you normally think of as a file system where you have files and directories, where you have applications that can access those files, either moving them around, renaming them, or reading them or writing to them. And so you expect to have something like a directory system with a big directory tree with files in these directories, and that the files and directories are accessible through standard file system streaming I/O type protocols, standard libraries that can access them. And virtually all major applications are written in terms of this. And certainly the common ones you'll use on HPC, high performance computing systems, will all use this POSIX compliant I/O will have that ability to do that. So whether you're using a scripting language like MATLAB or Python, or a compiled program in C or Fortran, or any of the standard libraries that these applications will use, they'll all have methods and functions that will use this standard form of I/O and know how to talk to this kind of a file system. And so that's what you normally get on something like a local PC. You'll have a file system with file folders and files within those folders. That allows you to read files in really flexible ways, read or write to them. It'll allow for fragmented access where you can seek into the file and read or write a small bit of the file, or read the file all at once. It's very flexible in how you use it. On MSI, this kind of storage is what we call our tier 1 storage, and you'll find your home directories, scratch space, and even there's the RAM disk, parts of it is accessible and can be used as this kind of file system storage, and I'll discuss each of these in detail. Now, the other kind of storage, and this is more modern, is objects and object store. And this is more forward-thinking in terms of scaling up to very large volumes of data and data that's accessible across the internet. It's organized in terms of what they call buckets and objects. A bucket would normally map to what you think of as a directory, since it contains objects, which you'd normally think of as files. I think they refer to it as objects because, in principle, you can set these file systems up in such a way that it's object-oriented, where you would have methods and applications that know about the kind of files that are stored there. And so the files would come with their methods, be associated with methods that know how to read and write them and maintain them. But generally, the way that we are using it nowadays, think of it as directories and files, because that's what it'll directly map to. However, on an object store, it gives you an interface for accessing it in ways that are not accessible on a normal file system. So you can, for example, set files up on our tier 2 storage, which is an object-oriented store, so that they're accessible over the internet through a URL. There's also an S3 interface that can be used for pulling and pushing data to and from this object store, and I'll be giving examples of that as well. And this tends to be very high performance, but the downside is that the access to the files is not as flexible. So you can't usually run an application and just read and write directly to these files that are in an object store. You need to pull them first to our tier 1 storage and then deal with them however you like there in the standard ways. However, since it has this modern architecture, it can be managed much more efficiently and less expensively, and can scale up to larger systems and allow users to have a much larger volume of data on our tier 2 storage, this object-oriented store, than we can afford to do on our tier 1 storage. And so that's sort of the trade-off. So think of this object-oriented store, especially as we have it at MSI, where it allows you to expand out to larger volumes of data. And I'll illustrate ways that you can use it in your workflows so that you can easily and with very good efficiency pull data off the system, process it, and then store the results, either on tier 1 or wherever you like. And this is our MSI tier 2 storage, as well as for the normal use. And we also have a tier 3 storage, which is tape for backup and archival type storage. And I'll mention that briefly as well. Now, also in general, there are pros and cons to the different kinds of storage spaces that we'll be talking about. And here I have a brief review of the hierarchy of storage that's available on compute systems, where the hierarchy is organized by its distance away from the actual compute, the thing that's doing the computing, whether it's be a CPU or a GPU. So at the very top of this pyramid is the actual processor that would be manipulating the data. And that actually does have storage associated with it, but you're not normally able to access that as a file system, because it will correspond to the registers and perhaps the caches that are local to the processor or the GPU. So it's the on-memory registers or layers of cache that would be on processor. This is very, very fast, but it's also very, very small. So it's at the pinnacle of this pyramid where you have the smallest granularity, but the highest performance. But at the same time, it's going to be the most cost on a per byte basis. And so that's where these arrows come in, where there's this trend that as you get further and further away from the CPU, your granularity gets larger. So you can deal with larger and larger volumes of data. You get more capacity. It's also cheaper on a per byte basis, but the performance is going to be going down. And so that's the trade-off. In yellow here, I have the different kinds of storage that you realistically can use as a file system on these different tiers, going from the random access memory, the memory that's on the node, to the local disk that's on the node, to the shared parallel file system that goes across nodes, to the tier 2 and tier 3 storage, the object-oriented stores. I've labeled these in terms of the POSIX compliant P or object store O in each case, how they can, this corresponds to how they can be used. And so I'll illustrate how you can actually access memory on a node and treat it as if it were a directory. And then put files there and read and write files to them. And this gives you excellent performance. But it's limited in its capacity because, of course, it's limited to the memory that's on the node itself. Similarly, you can, on the next stage out, there is local disks that all of our systems will have available. And this is typically available in almost any compute node at any center anywhere. At MSI, they're always on the new systems, there are SSDs, solid state drives. And again, they're can be treated as POSIX compliant storage. So you can read and write files in the normal way there with the directory tree, and all of your applications will run there. But they're local to the node, and they're going to be limited to the local disk, which typically isn't really huge. It might be a half a terabyte or so on the system. The parallel file system can be much more capacious, much larger. Again, it's file system compliant, but it's further removed because it's not even on the node where you're doing the compute. So it has to go over a network, and it can be a very efficient network like InfiniBand, but it will take longer in terms of latency and have lower bandwidth to get there. However, an advantage is with the new parallel file systems that we have installed at MSI, you can have many streams being read at once, and that can give you in aggregate even higher performance than the local reads. But that will be a trade-off depending on the application and also how much contention or competition you have with other users using the system at that point. And then further away, for larger volumes of storage and larger granularity and lower performance, is our tier 2 and 3 storage. And so I'll illustrate how these can be used efficiently in your workflow so you can expand out to accessing and working with larger volumes of data. And then finally, there's the internet and web access. And this can also be an important part of your workflow, but you would not normally treat this as or think of it as a file system, but rather you would access this kind of data through SSH type protocols, or maybe you're copying files from a local or a remote host, possibly accessing them via URLs or even an API for various repositories will accept that. So that's the overview of the general namespace and the kinds of storage that we'll be dealing with. And what that looks like here at the Minnesota Supercomputing Institute is that we have a variety of storage options available. We've recently migrated from the old PANFS file system to the new VAST file system for our tier 1 storage, which includes your home directories, the scratch space that you want to use, and also various ways of sharing the data with your group or with users at MSI more generally. So I'll talk about that briefly and how we're migrating off of that. And for the most part, we've migrated completely off of that, though there are still some storage in that it has been copied to on the new system that's worthwhile knowing about. Then I'll talk about the current user directories and go on to talk about the global scratch, which is also on our new VAST file system. And then I'll talk about the local scratch directories, which is usually an SSD, as well as the RAM storage, which is the memory locally on the node. And then I'll talk about the tier 2 storage and how that can be accessed in your in a variety of ways, including from your Linux shell as well as scripted and in jobs. And then I'll talk briefly about the tape storage that we have available, but that's usually more of a negotiated process between a research group an MSI because there's a contract involved, and you need to pay for this kind of service. Uh, and then finally, I'll talk about the storage quotas, um, and 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 how you can review those. So the old PANFS system, this was really state of the art at the time that we bought it, and it was well provisioned for the number of users and the size of the compute system that we had at that time. But as time went on, our user base grew quite a lot, and the compute power also grew. And also, as the system aged, it became seriously under-provisioned for the amount of use that it really needed to support. What's more, the policies that we had on that system, which were pretty generous at the time, and we felt we could afford it for the user base at the time, where we're giving user groups typically around 5 TB of data storage, led to some issues that were proved to be completely unmaintainable. Because it was great to start off with 5 TB of storage. You could basically have, all the data that you would usually want to start off with under your home directory. But it led to very poor or no data planning. You just basically started to accumulate data, and you didn't need to delete it, and you figured, well, it's under my control. I can manage it in my own way and delete it when I need to. The only problem with that is that as months and years started to go by, you started to have a harder and harder time keeping track of what you really needed to keep. You had maybe multiple projects. There might be multiple dependencies between these, and it became more and more work to even figure out what you could safely delete and not wreck one of your current one of your current workflows. And believe me, I'm as guilty as anyone with this. And it became a real problem in terms of data management. What's more, there were many groups, especially the larger research groups, that were sharing a large volume of data, but because of security policies, typically files that a user would create were not accessible by any other user, not even the PI. And then especially undergraduates or graduate students, when they would move on, would leave that data. The PI would oftentimes want to keep that data for ongoing projects, but the data would be essentially marooned because the user who had the permissions to access it and even give permissions to read it had left. And usually operations would have to be called in to migrate the data in one way or another. And this became a logistic issue, especially for larger volumes of data. So for a variety of issues, that kind of policies and that file system became unmaintainable for the very large home directories that we were allowing at that time. However, those old file systems are not going away. In fact, what's happened is they've been migrated to what we now call project space. And the intention here is that this is more properly managed and owned by the principals of the research group, who are going to be persistent and associated with a given project, so that they can responsibly maintain that data. So data does not get marooned, and it can be managed on an ongoing basis, even as people move in and out of research groups. And so that migration looks something like this, where in the old file system, and these old names are only really relevant for people who were working under the old system under PANFS, where you had home and then the group name, which would be usually the principal investigator's login name, and then your own username for your own home directory. And then there'd be a shared and public space also under the same group, and that kind of a hierarchy. And this is very practical at least getting started with, but we realized that the granularity of how you want to manage data was actually better if you thought of it not by a research group, but by project, because there can be projects that span multiple research groups and research groups that have multiple projects within them that they want different parts of their group to have access to and organize it in different ways. And any given group might have projects that come and go in overlapping sets. And this allows them to cleanly keep those projects separate. It facilitates that level of organization. So as a first step with the migration, operations migrated the home group directories under this new projects directory and project standard for the standard kind of storage, which doesn't have, for example, different kinds of security access limitations like that might be regulated by HIPAA or PHI type of data. And so this is basically for the standard data that doesn't have those extra restrictions on it. Any data can go, any of that kind of data can go under project standard. And then they just kept the group name for the initial migration. But the intention longer term is that these will be organized not necessarily by group, but by project. And then under that, usually for a group, you would have your home directory, the user. But this would be your old user space. So it's not going to be your current home directory. This is where your old home directory would have gone if you had been under the old system. And so it's not fewer and fewer new users are going to have to worry about this. But if you are in a research group that's been around for a while, then you will probably need to know about where their shared and public data had been migrated to. And the namespace is going to look something like this. You'll want to look under projects, shared, and then your PI's login account name. And then there you'll find shared or public. And more modern ways of sharing data it'll be organized by project. And so you'll have the project name here. And there'll be something for the PI and the people managing the group to come up with that namespace. So there's more flexibility in the new system and hopefully a better way of managing the data moving forward. For your own home directories, though, this dollar home will always get you to your home directory. Also under the Linux system, simply tilde will be a path that leads to your home directory. And so this is a simple way to reference your home directory, or you can just cd tilde and return, and you'll go to your home directory. The old home directories, if you were under that old system, there are shell variables that will support that too. Old home for your old home directory that was under PANFS and was migrated to VAST. Or the MSI project space, this new project space for your group. And there's details of that at this hyperlink here. Okay, so now we can get into the new home directories and what you're going to be dealing with in the environment now, especially if you're a new user. They're really all users under this new VAST POSIX compliant file system. So your new home directory will be on this VAST system. It is POSIX compliant, so you have a lot of flexibility in how you deal with the directories, and it's going to look very similar to almost any other computing system that you'll be familiar with. The persistence of the files is basically the duration of your account. And you'll be able to access these in all the ways that you would normally be able to access any files under a Linux file system. In terms of directories, with a home directory, you can have a directory tree that you can organize however you like for your own work. Shell commands like CP for copy, MV for move, RM for remove, and even grep and various other shell commands. Grep will search through files, for example, text files especially. all those standard Linux commands will work under these POSIX file systems. And so basically, it will also support all POSIX compliant I/O. So again, this is virtually any of these type of shell scripting languages like MATLAB or Python, or any compiled code like from Fortran or C that you may download or build yourself. The namespace will look something like this, where now these new on the BAS system, your home directory is going to be under user. There will be a partition number here, or a volume number, that will vary by user and group. And then you'll have your username here. You don't have to worry about guessing at what this path is, because when you log in to the Linux system, you will start off in your home directory. And if you ever set your current working directory to be someplace else, if you just type cd space tilde or just simply cd return, the default nature for cd is to go to your home directory. And then you can do something like a Linux command like pwd, print working directory, to see the path that's there. However, you can always get to this through $HOME. That shell variable will point to your home directory. Now, there are limits that we need to impose with this, and it has to do with those considerations that I'd mentioned earlier about managing the data. And what we've found to be maintainable is to actually limit the home directory to be much, much smaller than what we had before, typically starting off at something as low as 200 gigabytes. Now this, and 1 million files in terms of total file number. Now this can seem like a relatively small volume of data, and certainly most workflows, most really large workflows, would exceed this size. It's certainly enough to get started with. But if you need to expand larger, we'll show you the options you have for that, especially using the scratch space and also the tier 2 storage in your workflows. But the way I like to think of this space that's directly under your home directory is it's for your direct input. And so think of it like, how much data can you enter into the computer simply by typing, whether you're typing through some kind of a menu form or just directly a text editor and typing in. Even a good typist, an unimaginably fast typist, might type at 200 characters a minute. And at that rate, at 200 characters a minute, you could type for a decade constantly and fill one of those gigabytes, one of those 200 gigabytes. That's one way to think about it. So if you think of your own actual input, the actual ideas and information that you are actually entering in, and not data that you copy in, that is going to be much, much smaller than this. So it gives you plenty of room for that kind of information. So like your configuration files, your input files that are text-based and specify what the work is going to be. And so that it's plenty large enough for that. And you really want to point off to some other space and some other way of accessing the data if it's going to get much, much larger than that. And there's several reasons for that. One is that in order for this kind of these home directories, which are not only fully POSIX compliant and therefore very, very flexible, but also are backed up so that you won't lose the data that you input, and you can recover more readily. That is costly, especially once we get up to on the order of 1,000 research groups and 10,000 users. You multiply that out, it starts to be a larger volume of data that needs to be maintained, and maintained in a way that's almost, virtually always accessible when the systems are up and is safely backed up. as time goes on. Um, that's part of it. But there's even, I would argue, an even stronger incentive that an individual user has, and I include myself in this, that helps you if you're restricted to a smaller volume of data under your home directory. And it all goes around what you would call a data plan. Part of this is that in order to expand your research, you need to be able to treat the way that you access data in such a way that it's not only extensible, but you can automate it and you can record what you did. So rather than having the output of your work be a current set of data that's staged someplace, the output of your work that can be thought of more abstractly as the methods and techniques that you created in your imagination and then implemented in scripts and in programs to define a workflow that can manage any volume of data. Those ideas, in terms of shell scripts, in terms of programs, in terms of configuration files and inputs, are all way, way smaller. That the metadata basically that controls and defines the workflows is all way smaller than the actual data that's being processed. And in this way, you not only can make the job of scaling up to larger volumes of data easier in the long term, but also it naturally records what you did, makes it repeatable, and makes it much, much easier to do things like parameter space studies or controlled experiments. And so it facilitates all of those, just thinking about it in terms of not the actual data that you processed, but the way that you go about creating that data. So that even if it was all wiped out, you have the scripts that you can just run and create it again. If you can do that, your methods are repeatable. And you can also makes it much easier to scale out and do it again on with a different set of data. And so it has all those advantages working for it. And that's my argument for why actually it does us good to limit ourselves to a smaller volume of data for our home directories. But that doesn't limit your workflows because we have global Scratch. And each research group can have a much, much larger volume of data. Again, it's on this new VAST appliance, this VAST file system, which is fully POSIX compliant, very performant. It's visible to all of the Linux systems and has a persistence that basically will last at least as long as a month. After that, it might get purged. But that usually gives plenty of time for jobs to finish the job of pulling the data in, processing it, and then saving the results. And that's the intended use for a Scratch file system. So it's visible as a directory, and you can all the standard shell commands work with it, no problem. The namespace for this is all under scratch.global. And you can, under this, you would create your own directory tree, however you like. You don't want to put your files directly under Scratch Global, but what you would typically do is make a subdirectory directly under Scratch Global that would usually be something like your username. This will help keep it distinct from any other user. Then under that, you're free to come up with any directory tree you like and organize the data however you like in a deep directory tree system, and then access the data that way. Each group gets up to 40 terabytes at any one time on this, and you can check their usage with this group quota -R for getting the total usage that your group has on that. But usually 40 terabytes is enough. You can have up to 13 million files, and again, this is a limit by the group. And this same group quota -R will tell you both the total volume of data in gigabytes and the number of files that are currently being used and what the limits are. And then there's local scratch. And this is storage that's, again, POSIX compliant, but it's a different kind of storage rather than being the shared file system with highly rated disks. It typically will map to a single solid state disk that's directly on the node. And as a result, it's only visible to the node on which it's locally mounted. And it will, the persistence, the practical persistence that data has will be the duration of the background job that's accessing the node. Because once the job ends, then that node will be cleaned off to clear off data for the next job. So if you created any data that's on this local disk under local scratch, you'll want to copy it off. It's great for scaling out to having many, many nodes processing data at the same time, because each one of these disks is independently accessed. So multiple nodes running will not interfere with each other, but at the same time, they can't see each other's disks. So that's the trade-off here. Again, all the standard Linux shell commands like cp, move, and so forth, as well as applications, can access this in the normal ways. The namespace will look like this with scratch.local. You probably want to make, again, like global scratch, make a subdirectory that will include your username and then any path you like after that. Just to ensure that it's distinct from any other user. It's, as I mentioned, it scales well to many nodes running at once. And it's a good place to have as local scratch space. Many applications like MATLAB and a whole bunch of physics and chemistry and engineering applications sometimes will want you to configure in a local scratch space where they can operate, and this is a good option for that. Again, the limits are that it's going to be local to the local node. It's going to be limited to the size of the local SSD, which will typically be on the order of a half a terabyte. And it'll only last for the duration of your job, as I said. Now, going to even better performance capacity is the RAM disk. And just like all the other file systems I've been talking about so far, it's POSIX compliant, and so it will look like a normal directory tree. And just like the SSD, it's the local SSD on a host. It's only going to be visible on the host and will only have a persistence that lasts as long as your job. All the normal shell commands work, as well as POSIX compliant IO and applications. And the namespace for that looks like this, where you would start with /dev/shm. So this mount point is actually available. This path is actually available on all of our standard compute nodes as well as login nodes. But you have to remember that it's actually a separate physical place for storage on each different node. And under this, you would have some kind of path. You probably, again, if you're sharing the node with other users, might want to include in this path your username. And again, it scales extremely well. It has extremely high bandwidth and low latency, which is, it basically is memory speed. You only have the IO, because you're treating it as a file system, you just basically, the only thing between your program and this is basically the streaming IO that you typically use for pulling that data in, and it will have that properties, but you're not going to get better, lower latency or higher bandwidth through those libraries than off of this. The only trade-off is that you're going to be limited to half the size of the memory on the local system. And of course, it's only visible to the local system. And that'll typically be on the order of 256 gig on a typical half a terabyte agate compute node. And the scope, again, is it's just local to the node. Now moving in the other direction in terms of granularity, capacity, and performance is tier 2 storage. So and this is the first example where I'm going to be talking about something that is not POSIX compliant. It's an object store. And so that means that you're not going to be able to access it in exactly the same way or quite as easily as you can with your home directory, for example. Instead, you need to use either something like the S3 interface, and I'll talk about the S3 commands for getting at it, or you can set things up so that you can actually access objects on this, which correspond to files, through a URL. So you can access it even over the web. So it's visible to all MSI systems, and if you set it up with permissions right, you can access it across the web. And the persistence will be the duration of the allocation for your group. And this storage is intentionally managed by the PI of the group, or the person who's managing the research group as a whole. Because the idea here is that you'll be able to create data, and then in principle, the PI can manage it on an ongoing basis, even if you move on to another research position. And so basically, to access is by file only because it is an object store. It's organized in buckets. And so, for example, you have S3 commands and URLs, or you can use Globus to access it. And there are various clients that you can use on your PC at home for actually accessing this tier 3 storage. And all of this is explained in this URL down here. So the namespace for this tier 2 storage is going to look like this. It will start for S3 because it has an S3 interface, S3://, and then this will be the bucket name. And so the root of this bucket name will need to be created by your PI or the administrator for your group. And then the files that are put in there, or the object names. The S3CMD command can be run with a variety of options, such as MB for making a bucket, LS for listing what's in the bucket, get for getting data that's in the bucket, or putting data to the bucket. So it's great for saving and staging data for larger workflows. Each group is limited to 120 terabytes as a default. You can get more, usually by renting the extra space. And you can see how much you're using and how much is left by using this S3 info command at any Linux command prompt on one of our HPC systems, or on a login node. And then there's third tier storage, tier 3, and that's tape. And these are so far been LTO tapes. I believe the current generation is LTO7, though that keeps migrating with time. Each of these tapes can store roughly 6 to 15 terabytes of data, depending on how much compression you get, because it will compress the data as it goes to store it. And it's visible on all HPC systems. And basically, the way it's organized is that when you get a set of tapes, the data that's written there is guaranteed to be available for the next 5 years. And the reason why is that these LTO tapes keep improving and changing their protocols, and also tapes have a finite lifetime. And so the typical cadence is every 5 years they will renew the entire tape library and the version. And they're forced to do this to keep up with the currently supported level of LTO tape that's currently available, and that keeps changing with time. Uh, and so when your group gets this, they're not just getting tapes; they're getting tapes with a service that allow that data to be um, written from any of our file systems to the tape, and also retrieved from the tape just through Linux commands. You don't have to mount the tape yourself. They're in a tape library with a robot that mounts the tapes and does that reading for you. The price the last time I checked was around $450 per pair of tapes. And they get you always have to buy them in pairs of tapes for redundancy's sake. Um, the file sizes that are recommended for storage for good tape efficiency will be on the order of 1 to 1,000 gigabytes in rough numbers. And the latency for retrieving data might be anywhere from 1 to 7 days, because if there's a backlog of tapes that are being read, it might take a while before the tape reader gets to your tape. So even though the tape vault might have quite a large number of tapes in it, it has only a few tape readers, and it depends on the contention at the time. So it's a relatively long latency. So you want to really think of this more as backup or archival type storage. And it's really needs to, and it's not generally available, but a PI can put in an email to help@umn.msi.edu and start a process to make a contract for buying some of these tapes and getting this service. And so that would be the way that a research group would get started with this, because there's money in contractual commitments that are involved. But this gives research groups that have a long time research program going a way of making having archival space in a standardized way, if that's what they need. So here's a quick review of the major storage locations, their capacities, the way you can find out how much you've used and how much space is left on those systems, and also what the limits are relevant to, or what they apply to. So, for example, with the old PANFS system, it was by group, and you could typically get anywhere from half to 10 terabytes of storage, and group quota will tell you how to use that if you have any data in that space, and that will be under the project space now. On the new VAST file systems, especially for your home directory, this is relevant to the user, and you'd start off typically with 200 gigabytes only. And user quota is the command you would run from a Linux shell command line to find out what your current usage is and how much you have left, both in terms of the limit of the volume of data, 200 gig, as well as the number of files. And typically that's like 1 million files you're limited to. Global Scratch. This is also organized by group. So it's group quota -R for the global Scratch space. And all groups start off at about 40 terabytes. For tier 2 S3 info, you start off at 120 terabytes on a per group basis, and you'd use this S3 info to find out how much you have left. The local Scratch, it's more raw in the sense that it's not like a persistent long-term file system, but you can find out how much space is available and much left with something like a du-sh for finding out how much you've used under your current directory. if you're under that local scratch space. Or you can do a disk-free -H for human readable for finding out how much free space is still available on that partition. And typically that's going to be on the order of 1 TB, and that's going to be by job or by login session. And finally, the raw disk is very similar. You'd use DU or disk usage, DU or DF for disk free commands to find out how much is left. And that's just going to be half of the memory of the job is typically going to be the limit, which typically be on the order of 256 GB if you're on a standard compute node and using the entire node. And again, that's going to be relevant on a per job basis and also on a per node basis, I should say. So that's the overview of the storage we have available. And so I'll dig down into a bit more into the commands you can use for accessing that data and manipulating it and managing it. So we'll talk about SCP for secure copy, which is a great old-fashioned but very simple and oftentimes effective way of moving moderate amounts of data to and from MSI systems from your own hosts that may be elsewhere on the internet. wget, which is a great way to pull data from web servers if they support basically these unilateral pulls. There's Git, which allows you to, which is a great way for sharing data and storage across groups, as well as source code. And then finally, the S3CMD commands for access, and I'll be talking about specifically accessing Tier 2 storage, which is available to all users. And then finally, Globus, which is a web-based way of moving very large and complicated volumes of data between major sites. So in all of this, I'm going to assume that you have access to MSI Resources. And the standard way you would do that is to go through the university VPN. And then I'm going to talk primarily about commands that you can use on our Linux HPC systems, which are particularly relevant for larger workflows, where you might be running these workflows in jobs, where you needed to have gone to one of our HPC front ends, either through Agate login node or an on-demand desktop, to set up scripts and jobs for running these commands. And so the orientation will be assuming that you're logged on to an MSI system and you're running from the Linux command, which is relevant for our HPC systems. Starting out with secure copy or SCP, it's an SSH type protocol, and it's going to look very similar to the way you would log on to Agate itself. So if you're familiar with SSH, this should look pretty familiar in terms, at least the synopsis or the syntax of the way it looks like, where you do SSH to a username that's relevant to the system you're trying to log into. So this would be your MSI username and then the name of the host itself, in this case, agate.msi.umn.edu. So that's the way you would log in, and that's how, in fact, you'd get to a shell command prompt. You could also get there via Open On Demand Desktop. But I like to use this because it also illustrates the syntax that SSH type protocols are expecting. Similar to this, a secure copy, you would specify, especially for the remote host, the username that's relevant on that remote host, the host itself, and then you could give a path, and that's the syntax for this. And always with the SCP commands, like almost any copy command, it's organized in terms of two arguments, which is a source and followed by a destination. And so you would, if you are logged into MSI and you want to copy data to MSI, the way you would do that is you do SCP, and then you would give the the name of your remote user on and the remote host, and then the path that's relevant on that remote host as the source, and then the path that's local to the MSI, your MSI account here. So that's the syntax for that. The exact same command can be done with not just for individual file, but for a whole directory tree. So this path could point not to a file, but to a directory. And then you would want to use the -r flag. And then that would tell SCP to copy not just the entire directory and everything that's under it, again, to a path, and then it would reproduce that directory tree there. So this is an easy way for copying an entire directory tree. And this will work moderately well for directories that might be on the order of gigabytes in size. If it starts getting up to gigabytes in size, I should say, if it starts getting much larger than that, you might run into network hiccups, which stop the copy in mid-progress. And so this is great for moderate amounts of data, but I'll give you methods for larger amounts of data, especially with Globus. To copy from MSI to your remote host, it's really the same syntax, except that because now the remote host, from the point of view of MSI, which I'm assuming you're logged into, is not local. You need to give the local path first. So this is going to be the path that's on your MSI account, assuming you're logged. This command is being run at MSI. So you give the local path and then the name of your remote host, your remote user, your remote host, and then the path there. And similarly, the -r flag allows you to copy entire directory trees. wget is a handy one. It's very simple, actually. It's one of the simplest one to use, but it assumes that what you're trying to do is copy data from a server that is organized and set up so to allow remote access of the internet to pull data from it. If it has those permissions open and the service set up, and typically GitHub type services and many servers will allow this if they have data that they want to make available to a larger community. They'll give you a URL by which you can then access it. And on MSI systems, we have a command called wget, which makes it very easy to pull that data. Basically, if you're logged onto an MSI system and you're in a directory where you want that direct data to land, you would just do wget and give the name of the URL. And this will typically pull a tar or a zip file, which you can then unzip and process as you like. There's Git, and the university currently has a GitHub, which there's extensive documentation for the use of Git and the university GitHub in particular. This is going to be going away sometime in the next year. And so this is something to look into for whether or not you want to go down this route if you're starting something new. If you're in a research group that's been using this for some time, then they'll currently have a GitHub, then they may have a lot of data staged there, and we'll be needing to work with OIT for the correct way to migrate this data to the more universal GitHub Git that's available worldwide. And so that will be changing in the near future, but the details I haven't heard yet about exactly how they want to manage that. But currently, you can still run GitHubs, and whether it's from the university site or from a general GitHub, these commands should work for basically these Linux commands. I'm just giving the cartoon here of what they look like for git add, git commit, git merge, for ways of adding to the data that you have staged locally that you want Git to keep track of, committing it when you've made changes, and then merging it, or you can pull or push data. Um, and all of that is in the detailed in these websites here. Um, and then finally, for tier two access, we have um, the specific commands for accessing that storage. And so basically, um, you'd use S3 CMD type commands for like, for example, if you want to make a bucket, and so you do S3 and then give the bucket name here. The root bucket needs to be created by your PI or a designated administrator for your group, just so that the ownership is maintained for the group as a whole as opposed by the individual user. Once that starting point is created, you can then make buckets underneath that by extending the path of the bucket. And then you can put data to it with a syntax like this, where you give a file that's a local file on an MSI host, and you'd give a path to that file and then specify the bucket it was going to land in. Similarly, you can get data from a bucket by specifying the source first. So be the S3 / bucket name / file name, and then the directory where you want it to land. And if you can leave this last argument out, and it will just land in your current working directory. And then you can also list what the contents of buckets are. So that's a quick synopsis of how to use it. I've seen very good performance off of this. A benchmark I did quite a few years ago. I was getting over 1.4 gigabytes per second of bandwidth from 30 parallel streams using S3, just simply S3 CMD get. And that was back in 2018. It's much more it's much faster now. Now, for the most advanced and sophisticated way of moving data to and from storage, Globus is a great way to do that for accessing both tier one and tier two storage at MSI and moving data to and from it to remote hosts or between tiers one and tier two. And it really has all the properties that you could wish for if you have very large volumes of data to move. It has a web-based graphical user interface for specifying moves, and with a few mouse clicks, as I will illustrate, you can move entire huge directory trees, many gigabytes of data, terabytes of data even, and with deep directory trees. It will do it in the background, so you don't have to stay logged in. You can detach and just let it run in the background. It knows how to do retries and re-authenticate onto both the source and the destination hosts. And it will keep doing retries until it's done. Or if it runs into a problem that it can't get across, it will send you an email telling you that, or it will tell you when it's finished. So it really has a lot of good properties for migrating very large volumes of data. And so it's very handy for that. The university maintains, has a contract with Globus, and we have our own domain. And so that allows users to access Globus through your university ID. And I'm going to illustrate how you go about using this. And the starting point is this URL here, www.globus.org, for go to their home landing page for accessing these resources. And so you'd start on their home page. The look of this page is way different now. even over the first few years I was giving this tutorial, the amount of data that they said that they had been basically done the moving for, the amount of data they'd moved had actually more than doubled. And in fact, they don't even keep track of this number anymore because it's grown so large, and they've also moved on into all kinds of other services they want to highlight. However, it's important in the landing page for a starting point for accessing any of the services, and where you would start is this login, and that's going to still be in roughly this location here, the upper right. So you click on the login, and it will bring you to a page where you want to select the domain that your account is associated with. And they basically, since they're serving organizations across the globe, there is a huge number of domains that you can select from. This will start off empty, but if you click on this pull down, you'll see a very, very, very long list. You can scroll to University of Minnesota, which is the domain that, as an MSI user, you're guaranteed on having access to Globus through your MSI account. But what I find much, much easier is you can just start typing University of Minnesota, and before you get to the second den in Minnesota, it will filter it down to this item, University of Minnesota, which you can then select and then click continue. And if this is the first time you're doing it, or if you haven't done it in some time, you'll be asked to authenticate in to that service. Otherwise, the credentials will be cached usually in your browser, but they'll only be valid for some amount of time, usually about a week. That said, this login is, if you've chosen the University of Minnesota domain to authenticate in for using Globus services, this is going to be your University of Minnesota account and password. The same one you use for your email, the same one that you use to log into MSI. And so they will bring up this Sibboleth that'll be probably familiar. It will look different from this, but you'll be very familiar with it for logging into the VPN, accessing your email, and getting at MSI Resources. So it'll be the same one, basically, for that authentication. It will then bring you to a page where you can select Manage Data, and that will have these. The look will be a bit different, but all the functionality will be in the new format, where you have basically two endpoints that you'll need to work with, which correspond to the source and destination of the data migration that you want to specify. And an endpoint basically corresponds to a host that's on the web that has storage associated with it and knows how to talk to and is set up so that it can receive commands from the Globus Central website that keeps track of the data migrations, so that it can be set up either a source for a copy or a destination for the copy. So all of these endpoints basically are registered and set up with Globus to work with it, so that it can seamlessly migrate data across. You still need to authenticate into each endpoint for security reasons, obviously, so that people aren't putting data onto your account or stealing data from you. So what you would do is start by specifying the endpoint, and you click here on endpoint for one of them. And basically, you will get to a page where you have, again, a dauntingly long list of endpoints that are basically correspond to persistent endpoints that Globus is keeping track of. The University of Minnesota has quite a few, and they all begin with UMN, and MSI even has several for the home directory as well as tier 1 and tier 2 storage. And those endpoints for MSI will be UMN MSI, and then sharp home will be for your home directory. So if you were to enter that in, it will filter it down to just this one, and you can click on it, and it will bring you, if you haven't done this in a while, it will bring you to, again, a Sibboleth, which is will give you another opportunity to enter your University of Minnesota login name and password. Once you've done this, the endpoint will be activated, and you won't have to do this again until the lifetime of that certificate is expired. Under advanced, the typical lifetime is by default 1 day, and that may be enough for most of the transfers you want to do. If you want to do longer transfers, or if you're planning on using this endpoint repeatedly over the next week, you can go to this advanced and select a larger number of days, usually up to 7 days, for a longer lived certificate for activating this endpoint. Once you've authenticated in and the endpoint is activated, it will start off, since you chose MSI, UMN MSI Sharp Home, it will start off in your home directory. And so you can see the file, and this is a standard web browser file folder browser. So you can select these folders, open them up, and go as deep as you want to see what you have in your home directory, and select where locations to transfer data to, or sets of data that you want to transfer to someplace else. We then go to the second pane for if this is going to be the source, this will be the destination. So you need to usually activate another endpoint for the destination endpoint, and go through the same procedure to go to a second endpoint. Here I chose an endpoint in physics, and it's where I have a few folders already set up, and I can then select any folder or data here and transfer it over very easily. The example that I'm going to use is to begin with, is a small folder that illustrates the functionality that you get with Globus, where this is a little project I did using OpenFOAM software for doing some fluid simulations. I did a whole bunch of different cases, and I like this example for illustrating the power of Globus, because the way this OpenFOAM software works is that it uses the file system itself to organize a myriad amount of data and options that you can do with these fluid simulations. So each one of these top-level directories is a case where I was a study case that I was doing. And then inside of each one of those, it looks like this next level down, where you have places where you can specify various kinds of inputs, and also the output for the data sets, called sets here. And in that subdirectory, so another level down, it will typically store things in terms of snapshots of the calculation as it's progressing along. So you might have many snapshots there. And in each one of these snapshots, you have the values of the field variables that were that the simulation had during that snapshot. And so you might have many such files for fluid velocity, density, pressure, and derived quantities. And so the point here is that this ends up being a fairly irregular directory tree, 4 levels deep, hundreds of directories, and thousands of files. You could copy it all with an RCP, but it's a nice illustration for Globus to begin with. It's only about 0.6 gigabytes in size, but it was an initial quick test case that I started with. So to do that, to copy that whole directory tree over, all I needed to do is, once I had the 2 endpoints set up, is to browse to the folder that had the data and select it. Just click on it once and that will select it. Then select the destination folder for it to land in, and then click Go. you'll get a temporary message that basically is just telling you that the transaction was accepted. You don't need to worry about copying this directly. There are ways that you can use this long string to track down the details of the current status of the copy, but it's much, much easier to go to the activities thing. So this will disappear after a few seconds, but you can always go to this activities um, panel, and it will show you a list that's something like this of all of the copy requests that you put in. And so I had one here that actually failed, and then because I didn't set it up right, and then several that had gotten to work. And so this is the current one. So it's showing me in the order that they were done. By the time I finished futzing around and making slides and got to this point, it had already finished. It took about 3 minutes to complete. But I can still see what the status was by clicking on this down arrow. And it will show you a report something like this, where it will tell you the number of files and directories that were copied and the bandwidth that it took. Now, this was a pretty small copy with lots and lots of files. You know, over, almost 8,000 files and almost 500 directory folders, but a small amount of data. And with something that's fragmented, I didn't get an impressive bandwidth, only about 3.5 megabytes per second. But it still was very convenient to use. And because it's such a small amount of data, this didn't take very long to finish anyway. It was about 3 minutes. If you have more substantial amounts of data, and especially if it's organized in terms of larger files, you can get substantially better bandwidth. For example, if I move to 100 gigabytes, that's organized in 32 files, I got like 88 megabytes per second. And so that is actually a respectable fraction of the gig E bandwidth that this particular server in physics was hooked up on. Because the maximum of the protocol, gig E protocol, is 128 megabytes a second at 1 billion bits per second. But that's the maximum of the protocol. You don't ever get better than that, and typically it's less than half. But because this came across as a bunch of parallel streams, it actually could achieve a significant fraction of that protocol. Going to a better provision server, something that's on more like the internet 10 gig or 100 gig kind of connection, moving a similar volume of data, 220 gig, I actually got better than 300 megabytes per second. So you can move a lot of data really fast across the country using these protocols. And then finally, when each of these copies completes, you get sent an email with the details of the copy. And you'll get an email even if it fails and it figures that it can continue on, warning you that of the issue. Most typically, this is going to be because you asked for a very large volume of data and your certificate ran out, or maybe the server was just down. And so it'll warn you of that, and you'll get the final status in an email. So for my final example, I'm going to talk about how we can support very large workflows locally at MSI using our Tier 2 storage and using the S3 protocols, specifically S3CMD, for driving a protocol that takes really a large volume of data off of Tier 2 storage, migrating it to Tier 1 storage under the global scratch space, and then processing it there to produce a very small amount of data that maybe you could store on Tier 1 under your home directory. And so this gives you a workflow that basically reduces huge amounts of data to the small results that you want for doing your science. I'm going to be using job arrays, and I'm going to give the specific examples in some detail, but it's a very rich amount of options that you have available. And so we have on our website the details, much more in-depth discussion of job arrays and the options that are available, as well as MSI queues. And so here's a couple of links for that, for the pros and cons of the different queues that are available and what they're good for. So the basics for running it, the most simple kind of parallel job to get a lot of work done fast at MSI is a job array. This is perfect for data-driven workflows where the workflow is data-driven in the sense that you have many, many data items, and each one can be processed more or less independently. There might need to be a bit of organization for dicing up the work and specifying which files to be processed. And there might be some collection at the end which is usually much lighter weight because it's highly reduced processed data. But the bulk of the work can be done in these job arrays. And so I'm going to illustrate how to do that, and I'll use a specific workflow that is relevant to my own research that illustrates this. So generally, a job array will have, or any really a job that runs in the background, will have a job script. And we're using the Slurm batch script queue, and you can ask for resources in terms of these sbatch commands. And I'm not going to go into all the gory details of what these are, but you can specify the number of nodes. And here I'm going to ask for just one node, and the number of cores that you need to use, or CPUs, and the amount of memory, and the partition that it will be on. So it'll be at MSI. And then finally, you can have a log file that you specify. And you can go into much more detail with other nuances for this job request, but this is sufficient for this kind of a workflow. If you want other details for explaining what all these options are, that's in those links that I had on the previous page. This particular first example is going to simply just print out the Slurm array task ID shell variable that will be used to specify which piece of work a given task will do. And that's the secret sauce for how this kind of a construct can take a large volume of work that is maybe organized in terms of many, many files and split it up into different pieces where different tasks, which each one of which corresponds to a separate job that's running on a different node or a different set of cores on a node, how they dice up the work. And so basically what happens is that when you submit a job through the Slurm batch queue using this sbatch command and give it an argument with this dash array, and you can specify a range of numbers. Here I have 0 to 9 for 10 tasks that will be numbered 0 through 9. You can also give it like 1, 5, 10, 2, 3, or something like that, and it will put in those numbers specifically. But you can easily specify a range of numbers with a simple number hyphen number type of syntax. So 0 through 9, 0-9 will do it. And then I specify the script. So these lines are in this file, which is the job script. And that's all you really need to do to submit the job. And if you look at this in detail, all this is going to do using the Linux command echo is it's going to write out task and then give the Slurm array ID number, task ID number, that job got, as well as the node it was running on, so for the host name. And so it will produce, since I asked for 10 jobs, it will produce 10 different files. The namespace for the files are specified here under this it'll be under its logs directory, and then they'll have task, and then it'll have actually the job number that goes on with the whole task array. So it'll be one single job number that goes with the whole array, and then the task ID will be embedded in the name of the file itself. But importantly, that task ID is available through this shell variable, slurm underscore array underscore task underscore ID. It's available as a shell variable, which you can then use to specify what part of the work this task will do. There'll be 10 tasks, and they'll each get a unique number, as is printed out here, 0 through 9. And you can use that number to specify in any of a myriad of ways which piece of work they do. So the example that I'm going to use is some processing some satellite data. It's from the Sentinel-2 mission. It's basically taking a multispectral imagery over the entire globe with a repeat of every 5 days between the constellation of two satellites. And I'm going to be focusing on, they break up the data into a set of tiles that are like 100 kilometers on a side. And this particular tile is over, intersects Minneapolis area. So it's over Minnesota. And I'm going to look at the data collected over a 6-month period in 2020, back in 2020, May through October. And I'm going to focus on, just for this example, for the sake of this example, just looking at one band 3, which is the green band. So it corresponds to something that's close to green light, the peak of the what our visible spectrum is. Basically, the way that the repository is broken up the data is in terms of these tiles and the date of observation. And so the S2 corresponds to Sentinel-2 mission. There's A and B satellites for the constellation of two satellites. MSI here actually corresponds to multispectral instrument, not Minnesota Supercomputing Institute. But so this is their multispectral instrument, level 1, so that's top of atmosphere. And C it's been cartographically rectified. So that's been, after it's been mapped onto a coordinate reference system that's a pretty standard one, and here UTM coordinates. For this tile, we get one of these, basically a zip file. And so this has all the metadata as well as the imagery that was collected by the satellite broken up for this particular tile over this patch of land that's 100 kilometers on the side. And so the date is embedded in the name here. So this is the date of the when the data was taken, right down to the second, when the data take, as they call it, started. Because basically, as the satellite sweeps over the daylight side of the planet, the data take starts, and that'll be considered one full data take, and so that's where this number comes from. And then they have things like the level of processing, the orbit number, the tile, which specifies the location, and this is the data processing. All of this is superfluous, other than I get 88 of these files over this 6-month period, and they're neatly broken out. I can refer to the date in terms of this field here. Now, to break that up into separate pieces of work, there's a standard. I can do this in any of a number of ways. I'm using something the simplest way I could think of was using a Unix split command, which took that list of 88 files and breaks it up into 20 pieces. And this is these arguments, all they do is they specify that the sublists that it will create will be in files that start with X, have 3 characters that will go from 000, in this case, to 019 for a total of 20 files, and that they will have, they'll break it up by line, so I don't get half of a file name on a given line. And so each one of these files will then have either 4 or 5 of these files to do. So it more or less evenly breaks up the work to be done in terms of the zip files that are all stored on tier 2 storage. The Slurm job script that drives this then will look something like this. It'll be driven as a task array. And so it will take do that same sbatch -- task and then arrange. In this case, it'll be 0-19 for a total of 20 jobs to be submitted. And a given task will have the shell variable, slurm array task ID, that will correspond to which of the 20 tasks it is. It will make a directory that's based on that ID number. So each one of the jobs will have its own directory to work in to keep it separate from all the others. And then it will construct the name of the list file that has the zips that this one will work on, just as I had illustrated in the previous slide. And then it will loop over all the zip files in this list to pull using an S3CMD get command from the bucket. It'll pull the data from this bucket where I have the data staged on tier 2 storage, and it will just pull that to the local directory. It then will unzip the file, and then it will run a Python script that basically will analyze the file and get some statistics on this green band, or band number 3. And then it will clean up after itself. And I should mention that it's I'm using a Conda environment to process this data, because we don't natively have within Python the modules that know how to read imagery. I'm using a Rasterio Python module, or raster.io, that knows how to read imagery and do manipulations with it. Now, for completeness, the Python script looks something like this, where I'm loading this raster.io module. But the first thing is that since I've unzipped that file into this directory, I know the path, the nature of the paths as the subdirectory to find the imagery, in particular band number 3. And so I use this glob command to get the path to that file, and then I just split out of that to produce the fields that had the date of the data take that I mentioned earlier, to label the date on which this green band statistics is going to be reported. Then I'm using this raster.io utility to just read in the image as a Python array. And then basically I extract the good data out of it. I know that the way they formatted the data, 0 corresponds to no data. It's either usually it's because it's outside of the data take. Once they've divided it up into these squares, it's not necessarily inside the data take. It might only get a corner. So I want to get rid of that data. And then I use a Python NumPy array construct or method to get percentiles 1 through 99, including the quartiles in between. And then I report those with a simple print statement. When I submit the job, using this sbatch command with this dash array argument, 0 through 19, I can then list the arrays with and list the jobs that are running. And while it was running, I could see all 20 jobs running at the same time, processing the data in parallel. Once it produced that data and copied out to the 20 separate output files, which look like this list here, it's easy to concatenate them together and basically sort it by date to get these percentiles by date, which I could then plot up to get the variation of this green band through time. And so that illustrates how you can use Slurm task arrays and data that's staged on tier 2 storage to drive a data-driven workflow in parallel. And with that, I've covered the formal presentation, and I invite there to be questions.